Now let's begin. Okay, good afternoon, everyone, and welcome to the concrete construction presentation, where we will be discussing formwork, blowouts, pumping operations, and shoring. My name is Mohammed Adnan Imran, and I am the Assistant Chief of the Concrete Enforcement Unit. Presenting alongside me is my colleague, Eric Hoyt, who is one of the principal engineers within the concrete unit. Eric?
Good afternoon, everybody. Some of you probably recognize me from other areas, but I'm just going to start right off. We got a basic kind of a presentation right now that's going into what we do as part of the concrete enforcement unit, both inspection and in audits. First description here, we got a couple things that are going on. It's to provide an overview of the latest New York City Building Code requirements for concrete construction formwork in accordance with 2014. I mean, we've got another code that's coming up soon, but there's no solid date on that, so we're still going along with 2014 code for all administrative and enforcement procedures. Mainly chapters 19 and 33 is what we're going to be discussing here, concrete and safety. Case studies will be utilized to demonstrate the construction-related failures, incidents, and overall dangerous conditions commonly found by the concrete enforcement unit, including formwork failures, related neighboring buildings, and the general public safety. This, of course, will also provide participants with the guidelines on how to work with the concrete enforcement unit on design, construction, and special inspection issues. And so we want to be able to work with you guys. There's not a kind of thing where we're trying to challenge you to do stuff. We just want to make sure that you and the buildings, are done properly. Not that you need to be done properly, but that everything is done properly and we can all move on and have a good day. Now, we have the different pieces that are on. It's the learning objectives on here is that we want you to be able to review and be able to identify the 2014 Building Code requirements for formwork, for concrete construction, and for special inspections of concrete construction. These are three important pieces. And the last one is to review and be able to apply the 2014 Building Code Chapter 19 and related safety requirements in Chapter 33 as it relates to formwork and concrete construction. So we got, a couple of different departments or a couple of units that are in this department. And it's comprised of a forensic engineering unit, concrete enforcement unit, which is us, facade and local law unit, retaining walls, compromised buildings, and cooling towers. It's all part of the IES. So, general description is that we're a legislative unit responsible for all 5 boroughs, comprised of specially trained inspectors, engineers, and administrator, and we're all ACI trained and certified. The unit was formed in response a while ago to recommended actions in compliance with the High Risk Construction Oversight, or HRCO. Back before the HRCO, the DOB was mainly focused on 2 stages of construction. Development, which is pre-permit, and enforcement, which is post-incident. Something happens, then it needs to be enforced. Code conformance was placed in the hands of owners, contractors, inspectors, design professionals, basically all the guys that are doing the job. Over time, this responsibility was implemented less and less and less by individuals that were actually responsible for that. And that in combination with other things like a shorter construction cycle, 2 days curing rather than 7, and accelerated construction, trying to get everything done yesterday, it led to problems. Around about 2004, 2005, there were several incidents in the city that brought attention to some major factors, and it caused the loss of life and property. It was decided that certain construction operations would need to be kept in conformance and not to rely fully on enforcement after the fact. We want to try to make sure that doesn't happen, not what do we do after it happens. Then around 2007, HRCO was implemented in order to help prevent these kind of events from happening again. Several departments were formed, including CEO, to try to monitor the construction as it was taking place to make sure that it remained code conformant. Items like shoring, formwork, concrete strength, and structural design were inspected and reviewed by this department. So there's a couple of different things that we do over here. And one in the legislative responsibilities is field inspections. Structural inspections and site safety inspections of all buildings for buildings that are 9 stories and under are our responsibility. Our guys go out there and they make sure that certain catch nets are out there, that you have your means of egress, you have all that kind of stuff that's required for safety. So that's taken care of for buildings that are 9 stories and less. Now, once you get 10 stories and above, that starts being taken over by CSC and CSE, formerly known as BEST. So construction safety conformance and construction safety enforcement. They're now responsible for the major buildings, safety in the major buildings. Parallel testing. We do parallel testing where we go out to the field, our guys go out to the field, and we do tests like slump and, you know, with the cones and stuff, go out and see how much it spreads or how much it sags, and make cylinders that will eventually be taken over to Port Authority lab. They crush it, they see what the strength is, and then we compare that to what was being obtained by the TR2 labs that were doing the concrete testing for that job. We also are involved with the TR2 and TR3 referrals from industry and other DOB units. So the 2 major things that we're concerned with are TR2 and TR3, which is concrete testing and concrete, you might want to think of as concrete recipes as TR3. So legislative responsibilities. We have one big one that comes through, and that's we got to go out to these labs and take a look and make sure that everything they're doing is okay. So randomly we go out and about twice a year and inspect each of the New York City registered concrete testing labs. We check the staff management. We go and make sure that the people that are there are qualified, that their equipment and stuff is all up to date, that it's been inspected, that they're properly curing items. They're not just leaving stuff out the back porch until they're ready to test them. All this kind of stuff. These are all requirements that are going on. We also request all this information to be sent to us, all the records. We don't sit there the entire time and go through to see when everything has been inspected or calibrated. We have that stuff sent back over to us. We take a look at that and make sure that everything's hunky-dory. And if it's not, we keep requesting. So it's fun for everybody, but it's something trying to make sure that everybody gets the stuff they need to. All right. Now, engineering audits get a little bit more complicated. We have pre-permit reviews, which is rare. Sometimes we get calls from the borough. They say, hey, we want you to take a look at this. We don't like it, or just doesn't seem right, or for whatever reason is coming up. And we do a review on that kind of stuff and then give them back the information on it with what we believe needs to be changed or needs to be looked at more for code compliance. Then a lot of the times what happens is our guys go out to a job, they see something that's not quite right, and they bring it to our attention, or CSC and CSE bring it up. We've also had, you know, other departments come and say, hey, we don't like the way it looks and stuff. So we come over and take a look at the plans and different other objects and try to see what things may or may not be code compliant. The more we see, the more we look. And so that involves not just looking at the plans and making sure all the little pieces like your wind speed and stuff like that are up to code or according to code, chapter 16, I believe. But also the engineering design, gravity design, wind design, deflections, all that other kind of stuff. So we go through each of these individual things in order to be able to try to make sure that it's together, it's coordinated, all the individual things such as proper code years. The TR1 inspections are listed on there and they match the TR1s that are coming in the other. That's something we'll get to a little bit later. Everything is done properly. So this is an extension of the previous one. It's special inspections. That's what I was talking about with the TR1. We are also ones that are responsible for going through and looking at all these reports that come back to us to make sure the building was put together properly. And those things are needed to be done, put onto the structural drawings. You have each of the individual ones going through concrete, masonry, steel, welding, that kind of thing. And we compare to make sure that one matches the other and that everything makes sense. You have a big concrete building, you don't have concrete inspection, that's a problem. So concrete operations and construction, there's our 2 and 3. We got almost like a half dozen TRs that we deal with and stuff like that over here. So, you know, we're very popular with the TRs. But concrete strength reports and licensed concrete testing labs listed on the TR2, all the signatures, all that other kind of stuff. So you can reference ACI SP21 pack or ACI MNL 2019. So the legislative responsibilities, we have incident response as well. This is when something goes wrong. This is the tail end that we did, that the Department of Building did originally, that something fails and we need to go out. So Our major ones that we go to on those are formwork failures, concrete pump or hose malfunctions. We had one where the thing blew and shot concrete up, a couple of stories. Concrete truck accidents. Those are rare, but they still happen. Now, I'm sure all of you are familiar with these guys. These are our biggest friends and stuff that you're going to see a lot of for just a little bit longer. These are the classic TR2 and TR3 forms. These are all handwritten. A lot of the pieces come in, and generally speaking, if there's any mistakes on it and stuff like that, it's not going to be anything until we get a chance to look at it because something went wrong. So we look at this stuff. It's important to remember all these pieces because, and this is important right now, these are not going to be the ones that are used later. It's all going on DOB now. So if you were making certain mistakes on the handwritten ones and no mistakes came back, it's because it wasn't automated. You make the same mistakes on here, it's not going to be able to enter. So you got to make sure that you get the stuff right. Now that said, Mo's going to go through some of the more specific items involved with this, and I'll hand it over to Mo.
Thank you, Eric. The TR2 form identifies which testing lab will be performing the sampling of concrete and thereafter performing compression tests on the concrete cylinders. The testing must be performed by experienced inspectors certified by the American Concrete Institute or the International Code Council. The testing technicians perform acceptance testing on the concrete, which includes the unit weight, the air content, the slump, and the temperature of the concrete. It also includes a specific number of concrete cylinders for compression testing, which is specified by the engineer of record. It is important to note here that the TR2 is an essential item pre and post permit. Prior to permit issuance, the concrete testing lab must submit the TR2 form along with the trial mixture. The TR2 report is also required prior to sign off to certify completion of concrete pouring. This graph shows the number of TR2s filed from 2016 through 2020. We can see here that the largest number of filings has consistently been with new building applications, with alteration 2s coming in second, alt 1s coming in third, and alt 3s is last, which is indicative of the type of work which occurs with these types of filings. The TR3 form is a concrete mix design to be used on site. Like Eric mentioned earlier, it is a recipe of the concrete to be used. It's important to note that the TR3 is required prior to the issuance of the permit. A department licensed concrete testing lab must submit the TR3, and the lab must attach the trial mixture reports and the field experiment results. The TR3 form must be thoroughly completed, which includes all required signatures on the form, such as the owner, the design applicant, the lab director, and the concrete producer. Concrete unit inspectors regularly issue violations for missing signatures on both TR2s and 3s. These violations are usually accompanied by partial stop work orders. Therefore, it is imperative that all fields are completed by the required personnel. The concrete mix information will be obtained from the lab which designed the mix. These documents capture information about the strength of the concrete mix and identify the lab which will be performing the testing of the concrete. It's important to have all this filed before the permits are issued. This graph shows the number of TR3 filings from 2016 through 2020. Similar to the TR2 filing stats, we can see a pattern here with the largest amount of TR3 filings being with new building applications. Pre and post permit requirements for TR2s and 3s. The initial TR2 and the TR3 must be submitted prior to obtaining the permit. The final TR2 must be submitted prior to sign off. So who's responsible for the TR2s and 3s? The TR2s and 3s must be signed by two separate licensed concrete testing labs, each certified and qualified to provide the service. The same lab that designed the mix cannot be performing the field inspections. It's important to note here that the Buildings Bulletin 2009-26 clearly identifies this. Per the New York City Building Code, exceptions for the TR2 and TR3 requirements must all be met with the provisions found in Table 1704.4. It's critical that all four of these requirements are met in order for an exception to be accepted. To clarify here, 2,500 PSI or less is required for the design. 4,000 PSI or more is specified on the plans. In this next section of the presentation, we will be discussing concrete formwork requirements in New York City and looking at some case studies of formwork failures. Concrete formwork. The design triggers of concrete formwork are outlined in Chapter 33, Section 3305 of the 2014 Building Code. The concrete unit inspectors are trained to identify if and when formwork drawings are required for a structure and regularly issue violations for lack of these drawings or non-conformance with these drawings. These violations usually come with stop work orders which can delay a project's timeline, however, are necessary to ensure the safety of the workers and the public. Site-specific formwork drawings are a crucial part of concrete construction since technical design data is simplified and given to job site personnel in the form of drawings to be followed for installation of formwork. This prevents formwork failures caused by inadequate formwork components. The concrete unit has seen numerous formwork failures which were caused by a lack of adequate formwork drawings, causing the workers to improvise. Improvisation, when it comes to concrete formwork, can be hazardous since there are many components to consider for safe formwork construction, such as bracing, shoring, spacing, and rate of pour, to name a few. Formwork drawing exceptions. Exceptions are acceptable when there are slabs directly on grade or footings where the slab or footing does not impart any loads on adjacent structures. Proper formwork placement, shoring and reshoring is extremely crucial while the concrete is in its initial curing stages. Lack of proper bracing, shoring, and framing has proven to be hazardous to worker and public safety, as well as impactful on a project schedule. Failures caused by improper formwork construction cause major delays to projects as extensive repairs are usually required. Here we have an example of a failure which occurred due to a combination of improper shoring, bracing, and spacing of forms. We can see here that the freshly placed deck has collapsed within the site. At the same site, we see improper shoring, spacing, and configuration of ACE-20 support beams cause the wet concrete to collapse within the job site. This caused extensive damage to the slab and columns. The weight of the fresh concrete imparted on the inadequate formwork components, combined with the vibrations and added live load of the workers placing the concrete, overloaded the already inadequate formwork. Here we see the damaged top and bottom layers of reinforcement along with the wet concrete which fell during the collapse. This type of failure can be hazardous to the safety of the public and the workers on the site. This will also cause stop work orders to be placed on the job site to ensure that the repairs done moving forward are in compliance with the New York City Building Code standards and the public and workers are safe. This is an additional example of the same failure. Here we see the failure from the slab level, which shows the extensive damage caused by the failure. The workers were pouring the concrete using a concrete pump and hose setup when the failure occurred. This is another example of a concrete formwork deck collapse where some of the wood components from the deck failed and were caught by the horizontal safety net. Again, we see how inadequate formwork can cause a major failure. This photo shows a close-up of the previous photo. Here we have a close-up of the failure noted, which shows that the non-conformance with the approved formwork drawings caused the ACE-20 beams to fall into the horizontal netting. A combination of improper lap lengths of formwork support beams and improper spacing of these shore posts, along with improper connections of shores to beam supports, was identified as the cause of failure. Eric?
To continue on this, we've had a lot of individual jobs that have had the same problem. This is one of the ones that both Mo and I were on a while back that had a very similar problem as the ones that were up on the high rise. This is like ground floor. So you think that it's a lot more stable. You've got, foundation walls on either side of you. It's very sturdy, but they had, to put it nicely, a creative kind of shoring layout down in the basement that was holding this all up. And this is what happened. When you're looking at it from, kind of this point, kind of looking down at it, the entire floor was odd. It had a catch pool, it had all sorts of stuff. And then they put the posts in weird angles and weird positions that were not a part of the typical. They poured the entire slab. No one else had a problem with it except for here. Here's one of the shoring posts that they actually used on this, and you can see that it just snapped like a twig. It's gone. And this is steel, and the entire thing snapped off at the top. So, lateral concrete pressure. This is one of the things. This is a different subject that we're talking about. We went through all the formwork and stuff like that. That's handling slabs and that kind of stuff. Now we're going to horizontal. Lateral concrete pressure. There's certain formulas that are used for it. It's concrete is a viscous liquid. It has certain properties to go through in order to be able to kind of flow and get into those cracks. But that also makes it so that it exerts lateral pressure as it gets deeper into things. Now, concrete's a little bit different. It's a little unusual. It has some special properties that go on with it, such as curing and its own viscosity that apply to it. But it's also being pumped in. So there's also a head factor that goes into it. Depending on how fast you crank this stuff in, it's going to have a pressure head that's going to add to the load that your vertical forms are going to experience. So you can find the concrete pressure on 3305-323 and on table 3305-323. We're going to look at that here. So you get columns with ordinary work, normal internal vibration. The pressure is 150. You're starting that off as a base, plus 9,000 R/T. So that's the pressure assumed. And the limitation is 3,000 PSF for 150 H. So they're getting a particular thing to try to get a height of pressure that's going on with it. So there's a maximum limit that's going on with it that also has something to do with how fast the concrete's going in. There are other references that you can go to that will give you the exact thing in if you're doing more of a forensic, like what the heck happened. You can find out that way. This is a design value that is more conservative, trying to make it so it does not fail. Here's an example of what happens when you put concrete against something that's not designed in order to hold it. This building over here, the concrete got between it and the interior wall, between the intended poured wall and the unreinforced masonry wall of the neighboring building. I'm sure some of those jackets were on sale shortly after this. But in all seriousness, if you look at this, you can see the foam. This is very common. You're told that you're supposed to leave a gap between the two buildings and then pack it with non-compressible foam, and everything's hunky-dory. The problem is there's no formwork on the side. There's no stay-in-place formwork. You've got to have something over there in order to hold the concrete. Otherwise, you end up with, to put it nicely, some unintended alterations. All right. So here's the other side. It looks great. You have all the shoring, all these breakers and boilers and stuff like that going crazy. It's going up. Everything is there, sort of. But when you look at it and you start going around, you realize that whole section over there does not have anything more. It's going right up against a neighboring building. There was nothing back that you kind of peeked in through, and it was formed right up to the edge. And it poured in, and it busted out. This is what's going on with it. When you take a look at this kind of thing, this is what you see in a lot of buildings, either for walls or for floor slabs. A lot of times for floor slabs, they'll frame it right up to the edge and then put foam in between and use a neighbor's building as their stop, as their pour stop. So this is another no-no. All right. Other examples that we've seen, there's so many permutations of people being creative with their formwork. It's just absolutely ridiculous. Just when thought you've seen them all. There's an example over here where they start off on the areas that were out and had the room. They had some nice metal, formwork that was going on there. They could detach it. They had the tie rods going through, no problem. They started going up and they couldn't put them in anymore, and they had plywood because it's thinner and it goes in there easier. Unfortunately, you see it's kind of improv, as it was being mentioned by Muhammad earlier. He was referring to whenever the guys out in the field don't know exactly what will fit right, so they just kind of stick whatever in there. And they started putting the plywood formwork in there and didn't attach it properly. And if you look closely, you're seeing that the cover distance just getting a little bit larger, a little bit larger, a little bit larger. It's because the plywood is bending out. And this is something to look out for on a lot of job sites. Now, similar to the other one that was in the beginning of when I started with this section, this is one that did use formwork. It did use stay-in-place formwork, and the trademark name for that one is stay form. But you've probably all heard of that form. But it's the stay-in-place formwork. If you look closely at the photo on the right, you can see that it has this vertical bar and has some texture going left to right on it. So this indicates that there was something there, but something went wrong. There was concrete got in here, it blew out the wall. We have other pictures. We didn't want to like blow this up too much of the concrete spilling out onto the floor in front of it. When we went around the other side, we found out, after I was finished doing my hand modeling, we found out over there there were certain things that were not appropriate. I could actually take my hand, as you're seeing in the center photo, and put it between the individual layers of mesh. They weren't tied together properly. They were pushed apart relatively easily, so concrete could get through there. And the other one is, it's a little bit harder to see, but over on the right-hand side, they had large holes that they used in order to be able to tie those tie rods, poke those tie rods through. So if you're at about the same size or larger than the aggregate you're using on it, it's just going to flow. And it did, and it broke out the neighbor's wall. All right, this is another example of a building that we had right here in town that they were going through and they were pouring and everything was hunky-dory, but the guys that were going with it didn't realize that they were pouring much more concrete than what they should have needed for just the one little wall section. Then somebody said, hey, hold it, stop. You end up getting the slop and stuff like this coming out of here. So they found out, they realized they had a problem with their neighbor again. This stuff went down several stories, filled up the area, and then blew out the CMU wall of the neighbor. The lucky thing was that this was only an infill wall. So we didn't have any serious structural damage, but this still was not a happy day. Other examples that we saw of this kind of problem with the stay-in-place forms. Everybody loves using these things, but so many people misuse them that it's important that these things be looked at and checked by all parties before concrete starts getting put in here, because I can't tell you how many we've had with this. So this is an example right here of where it wasn't designed properly. There weren't enough ties for the main supporting rods, and they just bent. So that said, there's a couple more examples that we have of this, and I'm going to hand back over to Mo so he can go over a couple of them, the reasons for their failure. Mo?
Here we see an example of stay-in-place forms used in very close proximity to an adjacent building. From this angle, we can see the ties, the backing support rods, and foam insulation combined with the stay-in-place forms. Upon closer look, we can see that the spacing of the ties here is much greater than specified, approximately double the design spacing in some areas. We can also see that the lapping of the forms is much less than specified. Typically, the lap length is approximately 8 inches at a minimum between running stay-form sheets and a 2-rib minimum between stay-form stacks. These dimensions are usually required to be changed as the size of the structure being poured increases. The lateral pressure of the concrete must be taken into account when placing these stay-in-place forms. Here we can clearly see the spacing of the ties is much greater than required. The Formwork drawings show the spacing to be no greater than 16 inches. However, in many locations, the spacing exceeded 30 inches. This is a direct result of the damage caused by the improper stay-form configurations on the site. The concrete poured within the forms exceeded the capacity of the stay forms and bulged outward into the adjacent property stairwell, damaging the wall and seeping throughout the stairwell. This caused extensive damage to the adjacent property and required a significant amount of additional labor in cleanup correction. This is another example of concrete damaging an adjacent property due to improper stay-form insulation. Here we are standing within the bathroom area of the adjacent building, looking at the stay-form and insulation setup of the construction site. The wall to the bathroom was completely damaged by the lateral pressure of the concrete. The concrete poured into this room at a high speed and quickly covered the entire room of this property. This is a close-up of the damaged bathroom wall we saw on the last slide, and the stay form used on the blind side of the construction site. The stay form is installed vertically, which is not recommended. The ribs of the stay form should be running horizontally. Lack of ties and inadequate spacing of support bars were also observed here. And Eric's going to be giving us some more examples of concrete formwork.
Okay, so the fun continues. What we got is that 3305.3.1.2.1 is if you needed more periods in a code. But there's a use of existing structures to support vertical or lateral loads. Now, all the stuff that we've been talking about right now has been you're building a new building or you're doing a major renovation, you put the shoring posts in, you put diagonals in, everything's hunky-dory. Or not so much as you see when they don't do it properly. But it's all self-contained. Now, you still can do things, say like in an Alt-2 or an Alt-1, where you have an existing structure that's going on, but there are requirements for it. And now, I mean, it's a no-brainer, but it's surprising exactly how many people start playing the whole scarecrow thing. There's sadly too many people that will go in and not do this properly. In order to be able to use the existing structure, you've got to provide, the engineer of record, the applicant of record has to go in and has to check it to make sure that it can hold these loads. Most buildings are designed just for their own dead, lives, wind, seismic, water pressure, whatever the heck it is. They're designed for a lot of different things, but they're only designed for that. They're not designed for, formwork and 150 pounds per cubic foot worth of, stone to be. So it's important that anything that's being used for formwork that's already in existence, for supportive formwork or formwork you're pouring against an existing wall or anything like that. We've seen what happens when you do that with something that's not suited for it. You need to check it. Not only that, the secondary important thing is if you're using a neighbor's structure to start doing some of this stuff, and one of the more common ones is probably an example is stuff like party walls, where two properties own the same structure. You have to get permission from them. Not only do you have to check to make sure it works, but you just can't start using their property and their stuff for your construction. So reshoring. Reshoring schedule. There's combining the two words there. A reshoring schedule is a signed and sealed reshoring that shall be provided and maintained at the construction site. Just keep this in mind. Just about every document, almost every document you need is gonna need to be kept at the construction site. You got so many, it's not even funny. And when we go over and we start looking at a lot of these sites, we say, oh, well, where's your inspection report? Where's your plans, your signed and sealed plans? Now, everybody just keeps going, oh, they're over at the office, and the office is across town. So it's important that all this up-to-date information is kept at the job site. So you need to have the signed and sealed reshoring schedule there on the job site. Now, this exception, a separate reshoring schedule is not required when the shoring information is covered on the construction documents prepared by the AOR, applicant record. But here's the catch. Those documents still need to be on site. So they don't necessarily have to be separate, but either way, they got to be there. So here's a biggie, okay? So 3305.3.3.1, inspection. The formwork, including shores, reshores, braces, and other support, shall be inspected prior to placement reinforcing steel to verify it to conform to the construction documents and form design drawings. So you got to have somebody go in there making sure that the formwork fits the plans before you start putting everything else up on it. So it makes sense. Such inspection shall be performed by a qualified person designated by the contractor. So the guy that's doing the work, has to have somebody go in there to make sure that the work is being done properly. Nothing shall prohibit the concrete safety manager from performing such inspections where so designated. So you can't put in blockers. You can't, oh, well, he couldn't see it because we had X, Y, Z. No, he's got to see everything. Or she, I'm sorry, I'm saying he too much. But they have to be able to get at everything. Okay. Subsequently, inspection should be performed by such a person periodically during the placement of the concrete. He can't just look at the stuff in the beginning and just go, okay, bye peeps. They have to be there during the sequence to make sure that things are performing properly and that the concrete isn't being dumped from way up on high. We have had cases where they haven't brought the pipe down and it's imparted additional load onto a structure because they've been pouring it for too high. It usually happens in walls. So during and after concreting, the elevations, camber, and vertical alignment for formwork systems shall be inspected using telltale devices. This is just a fancy way of saying you got to make sure things aren't moving after you've poured it, because that's a bad thing to have, that you poured everything in there, all the weight's on there, now your building starts to move. So it can be as minor as your windows don't fit quite right, or it can be, or that your floor is not flat, or it could be major, you could have a failure because of that. Now, again, a record of all such inspections shall be kept at the site. See, I'm repeating myself again. And should be available to the commissioner. Now, the commissioner himself is not going to go out there and take a look at this. We're going to be the ones that are going on, acting as agents. So we go over in the name of, the commissioner and enforcement and stuff, and we're the ones who can make sure that this stuff is available. The names, now the last thing is the names of the persons responsible for such inspection. So the inspectors, the guys that are doing that, those names have to be on there. Okay, not only that, what is it? The foreman in charge of the formwork shall be posted at the field office. So we have to know who's responsible for all this stuff. You can't just, oh, the guy's not here. Okay, well, who is he? So 3305-332, formwork observation. In addition to the inspections by the contractor required pursuant to section 3305-331, visual observations of the formwork for the general conformance for the design intent should be performed by the formwork designer. Okay, that makes sense. Or an employee of the formwork designer under his or her direct supervision. So you can have, one of your co-workers or one of your subservients, or however you want to phrase it. You can have them going out and taking a look at it. But the person who is certified to do all this kind of stuff, they got to be out there making sure that they're doing it right. Same thing, you can have a registered design professional. You can have a PE going out there, retained by the formwork designer, to go out and do it for them. They can do it all by themselves. Or they can have one of their lackeys go out and look at it, but they got to be making sure that they're doing the right thing, because they may not be qualified for some of these items. So now, formwork observation exceptions. A formwork observation pursuant to section 3305-332. You don't need it for some of these elements. You can look at section 3305.3.2.1 in order to be able to get most of the unusual ones that don't require it. And in general, 1, 2, and 3 family dwellings don't really need it. Your little 2-story bungalow and stuff like that out in Queens, you're not going to need formwork drawings for. So that being said, I'm going to hand it back over to Mo so we can look at some of the responsibilities of concrete safety managers.
Concrete safety managers, they're an integral part of safe concrete operations in New York City. We are regularly asked, when is a concrete safety manager required on my job site? The answer to this question is, when a major building has a total of 2,000 cubic yards or more of concrete, a concrete safety manager must be on site. And this is noted in the Building Code 3310.9.1. Concrete safety manager's duties. The concrete safety manager must be present for all concrete operations. Concrete operations are defined as the pouring of concrete and the construction and stripping of concrete forms and all related activities. A concrete safety manager is an extension of the department and holds a license with us. The concrete safety manager must be registered on the PW2 form. The concrete safety manager is required to keep a daily log of all concrete operations performed on site. The department offers a reference checklist for concrete safety managers, which is available through the link listed in the last bullet here. We will also be putting this in the comments section at the end of the presentation. I'm going to hand it over back to Eric for improper shoring.
Yeah, this gets fun. This is where we're going to see a few more of the examples of things that should not have been done in certain ways. So this over here, this is a job that was, I'm not going to say exactly where, but it happened, relatively recently, a couple of years ago. And they were not following certain required design procedures or construction procedures. And some CMU came falling down from the building and literally ripped a hole through the ceiling. Luckily, the person that was living there was not in that room at the time. So this shows the example of the damage that was caused. When we went over to the building and took a look, you can see how high up we were. If you look really carefully, you can see kind of a footprint of where that wall section was, where that pier section was, and 2 little holes that are on it with kind of little damage. This is indicative of where the anchor rods used to be. So not only was this improperly designed. I mean, it was improperly anchored. There were several things that were contributing to it. But then when we started looking at the other stuff, we noticed these things were not braced properly. They weren't held in any way, shape, or form. Once the first one went, they went back in there and they started tying it up with rope. They were playing Cub Scouts over here and practicing their knots. So they're trying to hold up these little puny 6-inch CMU walls to make sure none of them fell over again, these infill decorative kind of pieces. But the one thing to actually take a look at, and it's really important with this, is that this masonry construction, they put on the outside of the safety elements that were going on with it. So this is not proper safety, not proper shoring, not proper construction. It's just too many things all at once, and it caused a failure. That led to a lot of examination of other things on this building. Now, talked about protection of buildings. Mo showed a slide earlier that had some of the formwork and stuff like falling off, and it's being caught in the catch nets that are going around a building. Now, for buildings that are not too tall, 75 feet, is that what it is? And so below 75 feet, you don't need those catch nets. You have sidewalk sheds, you have plywood protection for your neighbors and all other kind of stuff. Unfortunately, a lot of these places don't do that properly. So they went to all this work in order to be able to put up all this, planking and stuff like that on it. And then they decide to just leave that nice little awning that goes out over the side door, that aluminum kind of thing that you're seeing from, I think, the 1960s. That's not going to stop a brick from going through it. And on the back of the building is the same thing. It's an example that they just threw plywood over something and called it a day. These are important to notice that it's all integral. There's not one part that goes without the other. You got to make sure the stuff doesn't fall, and if it does fall, you have something to catch it just in case. Now, speaking of falling, we had this job, and this was interesting going out. We had a wind event that went on, which basically means that everybody gets that warning through their email if you're subscribed to it, which you should be, saying, "Hey, what is it? We're due for a strong wind. All construction people are advised to tie stuff down, batten the hatches, and stow the cranes, all that kind of stuff." So we had one of those wind events, and lo and behold, this one wall that was all the way up fell over. Now, there's a couple important things to note about this. We're talking about shoring and forming and stuff like that. If you look really carefully, the individual parts on that are holding up the wall on the right-hand side, there's only a single 2x4 that's holding up the wall on each end. So that was it. That was the whole thing holding up this entire CMU wall that was going up a good 8-9 feet. Add to it a couple things that we later found that the grout, when it was poured from the top, didn't go everywhere. So you have insufficient grouting that's going on. You can kind of see a couple of clean bars on the left-hand side that was taking care of it. So you got a good tall wall, ungrouted, no kind of shoring and stuff that's going on it. The wind comes over, blows it over. Now, it was kind of lucky that it had this impromptu shoring. You can see this stuff really doesn't work that well. If you want to do this kind of shoring, it's better to put it together where you have something that's going to be able to protect as a just in case. So after seeing all this kind of impromptu stuff being put all over, took a little bit more of a walk around, and you start seeing stuff like this. Now, this is an example, unfortunately, that I personally have seen at a number of sites. That everybody loves this new open web joist cold form steel CFS, but then they start going through and snipping it like crazy. So all you get left with is this little teeny tiny tab of cold form steel, this plate steel, holding up the entire load. So this is not what we're kind of talking about in this entire thing, but it's a symptom. It's one of the things that when CU starts seeing this out in the field, or we see similar things on the drawings, this is where we start looking further when these symptoms come up. So going back to formwork. Now, I mentioned wind events and battening down the hatches. This is another wind event that happened relatively recently. This wind event happened, and it just ripped the formwork right off. You can see the individual columns the column forms are tilted over, and those things are sturdy, right? So ripped it off, leaving bar going all over the place. The main problem is that most formwork is designed in order to be able to hold the design load. There's a specific amount of wind load that's prescribed for formwork that's less than a hurricane load, less than all this other kind of stuff, because the chances of you getting that amount of load during the time of construction is really low. So you do a little bit of probability, and it'd be too expensive in order to be able to try to shore this for Armageddon, if just for the construction. That said, when you start getting these wind loads and the wind warnings, you've got to tie everything down. If this thing wasn't designed in order to hold that load, you better make sure nothing rips off and lands on the street below, which is what happened here. So that's important to remember as well. Keep an eye on your notifications and make sure that everything is handled for that. Now, other things that are noticed with formwork that can kind of go wrong with it is just sloppiness. This one right here, it shows two individual items that were no-nos. One is they kind of just stuck the post underneath it. The bolts are not gone through it. It's not aligned. It's kind of just stuck up underneath there, probably kind of rubber malleted into place in order to be able to prop up and get that thing going. And then right to the left, you see this nice little 2x4 as a lateral brace. It's got one bent nail in it that's going nowhere, and a second one that's going through. One nail in order to be able to hold the lateral bracing. This is also a symptom that when you start looking around a lot of these kind of job sites, most of these 2x4s are usually only going in one direction. So it works okay when you're pushing in one direction, say in this example, left to right, it goes in tension, so you get a certain amount of strength out of it. But if it pushes in the other direction, they just buckle and go bye-bye. So you start seeing this kind of, slipshod assembly and just improper use. The guys that are putting this stuff up, a lot of them don't know what the heck is going on. They're not anchoring them properly. They're not putting them up properly because nobody really taught them how. So more examples, again, of exactly some of these sites and how they're going through. There's an improper lap on the one on the left that's not really attached very well. Going on it, it's just not good going on with it. And then you look at the right, and this is where you start getting creative again. That one post, I don't know if you can see it down at the bottom, but it was kicked out to the side because they had a hole in the slab. This is probably mechanical opening, for ductwork or piping or whatever it may be. So that was put in there, but they couldn't put the formwork in, so they just kicked it to the side. This is something that needs to be taken care of by the applicant of record, the engineer or the formwork designer. You can't just start improvising. Again, there's that word. You need to make sure that this stuff works. Sticking it in sideways and stuff has other effects, such as putting in lateral kick. It also reduces the capacity of the stuff and introduces other loads to the timbers and stuff, which it wasn't designed for. And then we could just get ridiculous. Your posts are not long enough. You don't do this. You have plenty of time to play Jenga at home. Don't do this. All right. So this is the kind of thing that the engineer should know about immediately. The inspector should be, going to shouting it from the highest mountaintop. No, this is a big no-no. All right. Because not only, maybe this will work for the load and stuff like that, but as soon as somebody walks by and hits it with a ladder, that's coming down. And here's just another example of what's going on, like the improvisational kind of stuff. Some people just don't know or don't care about how to put stuff together. These forms and these designs have to be done according to the manufacturer's specifications. So looking at this one, they just took like a standard, the 4-prong holder that holds a single in one direction and a double in the other, and they stuck a single through a double. So this is going to be wobbly. It's not giving the proper, confinement for the piece. And again, symptoms like this usually indicate that this isn't the only one. It's very rare that you only see one instance of this anywhere. So, like I said, this is an example of the improper shoring, and I'm going to leave it up to Mo right now in order to be able to go through some structural deficiencies that we're seeing on various job sites.
Structural deficiencies. Here we're going to be looking at a case where non-structural grout was placed within the columns of a structure. This building is a 40-story cast-in-place structure. The concrete placed on site was via a hydraulic concrete pump. Typically, at the beginning of a pour, the contractor places non-structural grout from the plant, which is used to coat the inner portions of the concrete pumps and hoses. This material needs to be discarded after its purpose is completed. Instead of the grout being discarded, it was placed within numerous forms of columns and some slab areas. As the structure went up and the loads were increased, the columns began cracking significantly and the rebars within the columns became visible. Here we have an example of cracks beginning to form in the columns due to added loads on unspecified and deficient construction materials. This is another example of cracks beginning to form in the columns due to the added loads. Here we see the cracks begin to form at the corners of the columns, which we observe throughout the site. We can see that the texture of the material does not seem ordinary or typical to a site of this size. Usually when you walk by columns within a site of this size, they have a specific texture and a look, and these columns look completely different than that. Here we see that the cracks are starting to get larger and starting to expand deeper within the column, exposing the rebars. Here we see major cracking of the columns and exposed rebars. The material does not have any aggregate in it. The TR3 concrete mix design, which was specified to be used, noted that 3/4 inch aggregate minimum should be used within the mix. This is a major error which impacts the structural stability of the building. Numerous issues took place for this to occur, beginning with the improper material placed within the forms and not being discarded, along with the special inspector not catching the issue. A concrete construction special inspector is required to be present during the entire concrete pouring operations to ensure the proper material is placed and the reinforcing members maintain their configurations as intended by the design engineer. To correct the issue, supplemental shoring was immediately required to be installed. As the deficient columns were all above the transfer slab, shoring was installed from the roof all the way down to the transfer slab. Investigation then began in order to identify exact locations and the breadth of the insufficient material. The investigation included coring, probing, petrographic testing, and visual inspection by the engineer of record. The EOR was engaged in the entire repairs process. Once all locations were identified, the repair design was prepared and submitted for acceptance. The repairs included installation of additional reinforcing and expansion of the columns using high-strength, non-shrink grout. The high-strength grout was tested during all placement operations to ensure the repairs were done as per the design. Here we have an example of the additional reinforcement which was required to be installed in order to expand the columns. You can also see adjacent to the columns the supplemental shoring which was required in order to safely support the load of the structure. Back to Eric for emergency shoring.
Yeah, we have one more example before we close this out. We're talking about temporary shoring now with the different things that are needed in the case of an accident or an event or an occurrence. Now, this was one job that I was working on. It involved, this involved, a shifting of the column. Architects like to take columns and structural columns and stuff and then move them around in order to be able to make it so that they have different spaces. Engineers in general, myself included, like to try to keep things going in a straight line, but sometimes that's not possible. So you take the column from above, you shift it over, and you make a nicer lobby space. That's fine. You put a transfer beam across, you thicken the slab, you do whatever. Problem was with this one, they didn't do any of that. So they got up to about the 7th or 8th floor, and all of a sudden the slab started cracking. And we're not talking just little hairlines and stuff like that. We're talking about a good portion of that slab started popping out, and that was a problem. So they needed to take care of it quickly, and they needed to take care of it. There's no joking. So they went in and they went to town with the shoring and stuff. Now, we looked at other pieces, little posts going in, little temporary, but shoring covers the whole entire gamut. I don't know if the retaining walls is going to cover some of that kind of stuff, or excavation is going to cover some of the things, but shoring is pretty much anything that holds up something else. These are huge HSS sections. You can see just by the size of the coffee cup down there. On top of doubled up I-beams, I believe they were welded together to form a box beam, and then spreaders underneath it that just spread the load out to take this. This kind of thing, it was something that was needed in order to be able to hold that load that was coming from above, because this wasn't the only place where we saw problems with transfer. Now, That said, we have everything shored up and stuff. They needed to be able to solve the problem. So here's another example of what needed to be done with the shoring on it. Okay, so they needed to go in. They needed to get rid of the slabs, and then they needed to take a look and see exactly, they needed to shore up the stuff that was remaining. So they didn't want to take out the entire slabs for various reasons. Load transfer, positive, negative moment, yada, yada, yada. So they weren't completely taken out all the way to the column edge. They were extended out. But you can't just leave them hanging. So if you notice on this one, they have shoring going all the way up now. So the entire opening they went around, they stuck all these things in everywhere, going all the way up the building. And they kept these in. And in addition to that, when they started repouring these slabs to fill it in, they put in additional pieces of shoring and stuff. So we're talking about shoring and formwork and stuff, these kind of things that need to be done in a building, but it's not just limited to pouring concrete. They apply to many, many other items, and several of them are also stuff that we deal with here at CEU. And we try to deal with all of them when we try to look at them from the aspects of not only just administrative, but also design aspects. So, I mean, I hope this stuff is understandable to you guys, that we came across and clear enough in order to give you a good idea of where CEU is coming from and what we do as a job.